Well, let's get started. So, first of all, welcome to our 2022 Technology Conference. And it is great that we're back in person. So very nice to see many people here again, and also new faces. So it's we've been doing this for 34 years now, and somehow it's exciting every time. We've got exciting things to tell you about. I think we've got exciting things to hear about from you guys. It's been quite a journey, and I think we're at a really interesting point right now. A lot of things that we and I have been working on for many, many years, often decades, are converging, very interesting places and lots of exciting opportunities. So it's kind of the big overarching story of what we're involved with is kind of the development of the computational paradigm, which is kind of the big intellectual paradigm, I think, of the 21st century. And we've been lucky enough to be kind of in the middle of the development of that. And in a sense, the big intellectual kind of arc that we've been on is to make a language to support the computational paradigm, to make a language that is the way of expressing computational thoughts, that is kind of the bridge between what is computationally possible out there in the sort of computational universe of all possible programs and computations and so on, and what we humans think about and care about and so on. In a sense, I view what we're doing as a kind of a little bit of an analog or repeat or something of something that happened 500 years ago, which is before 500 years ago, if you were thinking and talking about math, you would be doing it in the common language of the time, whatever it was, Latin or whatever, but you would just be using words in natural language. And then people had the idea, let's make a notation, a systematic notation for doing mathematics, mathematical notation, and that was the thing that spawned the development of algebra and then calculus, and basically made possible the mathematical sciences and a lot of the kind of current paradigm of the exact sciences. So we have this actually much more powerful paradigm in computation, and the challenge is to make sort of a systematic notation that supports that paradigm. And that's what I see us trying to do with Wolfram Language, trying to build a computational language that is a notation for this computational paradigm. And we've gotten a long way with it, but it's been a long journey. We've had to build this very big tower. For me, it's kind of been a sequence of alternations between doing technology development and doing basic science, learning from the making tools and technology development that make it possible to do the basic science, using the things we discover in basic science to figure out what to do further in technology. It's been kind of a great journey building this kind of tower of ideas and technology and so on. You know, if you look at kind of the history of computation, first we have computers, and then we had to, back when I started in this business, the only serious language you could use to interact with a computer was assembly language. But gradually, programming languages became more popular and so on. But the concept of programming languages had been take the computer as it is and build from the computer as it is and make it possible for people to control the computer as it is. In a sense, our objective is the opposite of that. Our objective is start from the world as it is and from the ways we think about things and try and represent those in a computational way that, by the way, we can then automate and delegate to a computer. So whereas the programming languages have tended to build up from kind of what the computer can intrinsically do, and then there's a small language, there's often a bunch of libraries that get built on top of that. Our goal has been to start off from sort of this whole conceptual landscape of things that we are interested in and that exist in the world, and represent those computationally so that we can then make use of the computational paradigm and, by the way, delegate a lot of the things that we have to do to computers. I think one of the things that's important that I like to emphasize about Wolfram Language is, well, first of all, this really, to my mind right now, the thing that we have been building towards, and I think we are very much achieving these days, is this goal of making kind of a full-scale computational language, a computational language that can represent all the kinds of things one's interested in a computational way. And that's the thing we've been building towards. That's where we're getting. Now, that computational language is important both for us to communicate to computers what to do. It's also important for us to have a notation, a language like mathematical notation, in which to express computational ideas. And this is something that I think will be increasingly realized to be important about what we've tried to build with Wolfram language. It is the notation that should be used for all these emerging computational X fields. It is the way to express oneself, to talk about the things one's trying to do in these computational X fields. It's an important point about it is that one might think, you're making things computational, you're going to start from the computer, you're going to learn computer science, you're going to do all these kinds of things that kind of deal with traditional programming languages and so on. And then eventually, after you've taken 5 courses on that, you get to the point where you can do computational X for some value of X that's interesting to you. What we're trying to do, what we've been trying to do, is to build kind of this accelerator that goes right from the beginning right to computational X without going through all those intermediate steps of kind of working in the sort of low levels of what computers do. And that's kind of been our objective, and I think that's something that we're seeing work. I mean, I have to say, when it comes to sort of the computational paradigm and development of science, it's been pretty interesting to watch. I mean, I think we've kind of seen multiple kind of epochs in the development of modeling in science. I mean, the first epoch long ago, antiquity, people were sort of interested in what are things made of? What is the structure of things? Are things made of atoms? Are things made of this? Things made of that? What are things made of? Many fields of science are still in the what are things made of stage. I mean, if you look at lots of areas of the life sciences, that's what is the main thing one still talks about, is what are things made of? But then after that, sort of the next big advance, which was made possible by the invention of mathematical notation, was the mathematicization of science in the 1600s, in the late 1600s, this idea that one could write mathematical formulas to describe how things work in the world. Big idea, that's what launched the mathematical sciences, sort of big story. What has happened, what I was much involved in the 1980s, was this idea that when you're making models in science, that you should use programs as a sort of more general thing than mathematical equations as ways to make models in science. And I'm kind of telling this in something of an allegory, because in what happened there is at first people were like, oh, no, we don't need programs. We have all these mathematical equations, all good. But then if you look now, today, 20, 30 years later, turns out if you look at new models that get made of almost anything, they're made in terms of programs, not in terms of equations. That's and that's been a sort of silent kind of process of kind of the overtaking of the mathematical paradigm with this computational paradigm for modeling. I might talk about later. I think one of the things that's been exciting in the last couple of years as a result of our physics project and so on is we have another paradigm, the kind of multi-computational paradigm, which is kind of a 4th level of this kind of progression. Maybe I'll talk a bit about that later. But in any case, the thing that to really say here is this process of kind of having things be thought about computationally. It's a process, at least in the case of modeling in science, it's worked. This is the thing that's worked. Now, one of the things that happens as we look at, I've been in this business a long time, and, I kind of get, and I also study history quite a bit, and it's kind of interesting to see these kind of waves of how ideas kind of come in and so on. And the good news is, we're very much on the right side of history in terms of the things that we're doing with building our computational language and so on. The bad news is it's an artifact from the future. We're probably 50 or maybe even 100 years ahead of where kind of it's widely understood that, oh yeah, this is the way to do things. So, what's been interesting is we built this kind of tower of sort of science and technology and so on. Actually, that distance between what is, oh, everybody understands this, and where we actually are has gotten bigger, which is actually very sort of intellectually satisfying. But it's also something where, in terms of you all and many other people, it's kind of neat, because you get to take what is essentially an artifact from the future, bring it into today, and do things with it that seem like kind of magic to many other people. And that's a really, it's this sort of superpower that we get, use Wolfram language in field X, making computational X. You have a superpower that is kind of a thing that you get from the future. Now, these timescales of people understanding things like the notebook paradigm. Okay, that took a quarter century for people to understand, even though I think it's a pretty straightforward kind of idea. The idea of symbolic programming, we're at, let's see, 43 years ago is when I first introduced kind of ideas related to that. And we're still at the kind of, I would say, still at the early phase of really broad understanding of that. Yet it's the thing that enables everything we do in Wolfram language, and it's been an incredibly powerful thing. So it's kind of that's the exciting thing is that we get to play with the future. The slightly frustrating thing is, and the opportunity in a sense, is we have this kind of superpower from the future. Now the question is, well, okay, the world will be greatly helped if other people can make use of this as well. And one of the things that I see as our biggest challenge right now, we've gotten pretty good at building the future, so to speak. Our biggest challenge is in spreading what we figured out from the future, so to speak, in the present. And that's a place where I certainly hope that we can count on. I know many of you have helped us a lot in this regard, and we need a bigger army, so to speak, to actually communicate what we know is coming from the future to today. And I'll talk a bunch more about kind of the ways that we're trying to contribute to this sort of communication of what's possible from the future to today, and ways that you all can perhaps help us and be involved in that. But well, so it's all right. So I've talked a bit about kind of the bigger picture of sort of make everything computational, the goal of making our full-scale computational language, and where we're going with that. Let me now turn to some very practical things. Let me start talking about, so what have we been up to in the past year since our last conference and so on? What have we been doing? Well, we've been doing all kinds of things. I would say that one thing I should say is I'm just going to give a small dusting of some of the things we've been up to. There'll be talks the next few days in much more detail by many of the people who've been involved in building all of these things on the ground, so to speak, talking about many more details of what I'll kind of give a few indications of here. But the last year's conference, we were just heading for the release of version 13.0 of Wolfram Language and Mathematica, released on December 13th of last year. We are planning to have 2 releases per year. We released version 13.1, which is a very big release, rather huge release actually, June 29th of this year. And version 13.2 is now in beta, and we hope to release it fairly soon. It will be a smaller release than 13.1, which is not saying much because 13.1 was an absolutely monstrously huge release. Okay, so I'm going to talk a little bit about things that have been both in 13.1 and are coming soon in 13.2. Again, those of you who we've had lots of presentations about version 13.1 out and about, and you'll find a post from me about kind of outlining what was exciting in 13.1 that came out in June 29th of this year. But I'm gonna recap a few of those things here. All right, so let's get going here. Well, what kinds of things? So we've been last few versions. So one of the things we like to do is over time, as we sort of make the world computable, there are different domains in which we make things computable. Many years ago now, we made images and image processing and things with images computable. In more recent times, we've worked on audio and made that computable. The next obvious thing is video. And so in the last few versions and in 13.1 and 13.2, a lot of progress in making video computable. So let's try something there. Let's try video capture, for example. Let's see if this works. And hello there, let's capture a video. Let's see how goofy that looks. Okay, there we go. We got a video. All right, so let's see. Oh, we can play the video. Yeah, just to prove it really works. Actually, it's a big deal that it works in Notebook here, that you can actually play it directly in the Notebook. we can take this, if we wanted to, we can say, take that video and just make 5 frames, take out 5 frames from that video, and we can go and do processing on that. And by the way, we use this. So for example, I do a lot of live streaming, as some of you will know, and we absolutely routinely use this kind of video processing on the live streams, and this is how we produce all of the material that comes out of the live streams. But let's try sort of mixing, let's say, functional programming with video. Let's take this, let's see, what was that, line 66 there. I'm going to try and do a video map time series. So this will take the mean of the image. So let's see what this looks like. Okay, so there we go. So that's showing the RGB values, RGB levels for the successive frames of that image. And I think it's, what we're doing here is we're taking videos and now making them things that you can just pick up and manipulate, just like you could manipulate, algebraic expressions long ago. So let's talk about, so there's also a lot of synthesis of videos that you can do. So let's take an example here. You can, one thing that's really useful is being able to synthesize videos from animates and manipulates and so on. But here's a slightly different thing. This mixes a few different modalities. This finds the image bounding boxes in that picture of elephants and zebras. Okay, so now let's go here and let's try and take that result. And let's, in that image, let's, I'm using my mouse here. Let's try and make a tour video that is a tour of that image visiting, let's see if it succeeds in doing this, visiting, let's see, it should visit the zebras and it should visit the elephants. Okay, so that's an example of again, we're kind of mixing machine learning kinds of things, picking out those entities in the image, together with the synthesis of a video there. Okay, let's turn to some quite different things. So let's, you might notice at the top of this notebook, there is a toolbar. This is something that we've, this is the beginning of a big framework. So it's just, this is a kind of contextually defined toolbar that allows you to do, well, all kinds of things. I mean, I could just take this and I could go here and I could say, let's make that background. What do I want to make that background? Let's give it a light purple background and so on. This is this is a big, oops, I should have committed to take that. This is sort of a big adventure of user experience to make a convenient way to do all of these things. And that, let's see, I want that background there. Yes, good. And to give you kind of immediate access to lots of things that are useful from this toolbar, this is kind of our way of doing that. And you'll see all kinds of things, whether it's entering a formula here that could be a tech formula. That's been a new feature for a couple of versions here, the ability to enter something in tech and have it be taken as Wolfram language input. So a variety of things up there in the toolbar, but this is just the beginning of all the capabilities that we will now be able to provide in a contextual way through the toolbar. Not to the toolbar, I can't. I don't believe the toolbar is zoomable. It might be, but I don't think it is. Anybody from UX here who can tell me the answer to that? I think the idea is the toolbar is for the person, what's that? I am. It doesn't zoom. The toolbar is intended for the in-person. Anyway, let's see if I can. Okay. Oh, okay. I should go to larger. Sorry about that. Okay, there we go. Let's do that. All right. Yeah, I could do that, but then God knows what the whole chain. The good news is, open up any Wolfram notebook with a modern version. You too will see this toolbar. All right, let's let's keep going here. Let me talk about, I'm going to move through lots and lots of different areas, lots and lots of different topics. Next thing I want to talk about is a language convenience kind of thing. One of the things we're always interested in doing is trying to identify. I mean, I view my job as a language designer being figure out what kinds of computations we all want to do, and then see which lumps of computational work are repeated, and then gives names to those things and provide those as things that one can easily do. So this is something which I kind of had always found a little bit frustrating, but I'd never really quite internalized what we needed to be able to make this work. So we have this notion of listability that's been there forever. You take two lists, 3 elements, you add them together, it'll add the corresponding elements. Okay, let's say we have a list like this, where we have a list that goes like that. What that will do is it will add the X to the first element of that list, the 1, 2, and the Y to the second element, 3, 4. Okay, what if you wanted it to go the other way around? What if you wanted it to add the X and Y, if you wanted to thread the X and Y into this so that they are being added at the second level, okay? That's something that this doesn't immediately do. But what we did was to introduce this new symbolic construct called threaded, and threaded does that. A simple thing, but very useful. I mean, what threaded does is you have kind of a tensor, and you're going to, and normally with listability, you're kind of making things correspond at the top level of the tensor. What threaded does by default is it makes things correspond at the bottom level of the tensor, or you can specify different levels of it. So, for example, let's say we do this, and then we go ahead and thread. So we can here we're multiplying by threaded of -1, 1. So what this will do is it will make each sub list there be, minus plus. Okay, very useful. Simple, very useful. The challenge is always to take things like this and turn them into things that are simple enough that one can kind of remember how to do it and so on. So let's give one more example here. So this is now sort of a 2-level thing. We're threading AB in there at the bottom level, and then we're adding XY to the top level, so to speak. Okay. That's sort of a language feature worth learning about because it's really useful. Let's talk about another different direction. This is a kind of a modernization story. When it's about characters. When in the 1990s, there were all these issues about different character sets and different languages and so on. And then this thing called Unicode got developed. We were quite involved with Unicode from very early days. And then Unicode filled up with 65,000 characters, all the languages of the world. And then it started spilling over to more planes of Unicode. It's just a big piece of structural change to make it so that all the different kinds of operations that we can do within Wolfram language work beyond plain 0 Unicode. So this is an example of sort of a piece of character space in ordinary plain 0 Unicode. But now we can also go to different parts of character space. So this is this is compatibility with a kind of that's cuneiform, which is not in current use, but depending on what exactly you're doing. But this covers the main thing is the sort of structural software engineering of being able to deal with these other kinds of characters. Now, another big thing that lives beyond plain 0 of Unicode is emoji. Those are a very different market from the cuneiform market, I think. But although, we're back to hieroglyphics now, so who's to know? So you can kind of manipulate those things. Now, there are very weird things in the world of emoji. Who knew that you can take the outer product, basically, of some emoji, and what do you get? You get these. I mean, this is in my opinion, this is a piece of semantic insanity in the construction of emoji. But there they are. Okay, so let's turn to a different kind of thing. This is now a UX story. If we've got, let's say we generate a big output. One of the things we've added in version 13.1, 13.2, I lose track recently, is, you get this big output. What are you going to do with it? What we've done is, and you'll see this on in a bunch of different places, is sort of this kind of attached cell that gives you things you can do. So for example, you could say store full expression in notebook, because otherwise all that's in the notebook is just that little fragment that you actually saw here. Another thing you can do that's pretty useful is to say iconize it. So let's say iconize expression in place. That turns it into this icon form, and we can pick that icon up. We can say length of that, it'll say 100,000 and so on. So we're trying to, iconization is this very nice mechanism that we introduced a couple of versions ago that allows you to store a big pile of data right there in your notebook, but not have to have everybody actually see it every time they look at the notebook, but just have it be there so that you can manipulate it. And increasingly, we're giving you sort of a hook to turn big things that come out and so on into those icon forms. Okay, next thing. Let's make a random plot here. Okay, now we can scribble on this plot. Okay, so let's go back to our toolbar here, and let's press, if you can see it, the scribble button. I think I might have to select it. And I press the scribble button, and now I get, at the bottom of this, I get an attached cell, and I get to start scribbling on this graphic and annotating the graphic. If I take that graphic, I can then use that graphic again and so on, and I could take it apart and look at its graphics primitives and so on. That's a feature that actually, back in the 1990s, when we first built kind of the symbolic graphics language, we thought this would be a feature that would be one of the most important things in there. Didn't turn out to be that way, but now it's something that with the canvas mechanism that we introduced a couple of versions ago, this becomes a useful thing to do. All right, next thing I want to mention is let's talk about trees. So we introduced a couple of versions ago, we introduced trees as a kind of native data structure. This is just a tree of a tree of a tree. If you look at the internal form of this, it's just a big nested thing of trees. Now these trees can represent their different branches using associations so that you tag the edges in whatever way you want. And for example, now we can also, let's generate a random tree here, something that was new in version 13.1. Well, actually, one thing we can do here is just make an unlabeled tree. Sometimes you want your tree to actually represent something where there's actual data in the tree. Sometimes you just want an unlabeled kind of anonymous mathematical tree. Okay, so then another thing has to do with, you've got a tree, you want to make it, I should have done a different tree. Okay, what I was trying to do here was to make this tree, let's do this. Let's say blank, blank, blank. 1 goes to red. Okay, there we go. So what that's doing is it's saying make the tree element style such that tree elements whose positions in the tree are any sequence of branching directions ending with a 1, make all of those red. So this is a general mechanism for basically styling trees. Okay, moving along with version 13.1, and I'm just sort of giving you a few areas that just to give you a sense of what's there. Completely different area. This has to do with dates. So dates, you would think a date is a date, it's rather straightforward. It's not. Dates are really complicated. And over the course of time, we've very completely filled out how dates work in different calendars and this and that and the other. Okay, the question is, you add a month to January 31st, what date should you get? And so this is something that we sort of worked out for version 13.1. This is roll forward, you get March 1st, you could get different things. This is, we've now really finished, I think, the sort of making dates computable in a useful way. Okay, turning to a different area. A lot of people use Wolfram language and Mathematica to do math and math education and so on. So one of the things we wanted to do is to make sure we really cover sort of all the things that happen in, let's say college level math. So here we've got one thing that was sort of left out, something that Wolfram Alpha has been able to do for a while, is implicit differentiation, differentiation along a curve, things like that. Part of the reason that we hadn't had this for a long time is because when we put things into the language, we want them to be really robust. We want them to really handle the general case, so to speak. It turns out the general case of implicit differentiation is not particularly easy when you have multiple variables and things like this. Anyway, we finally kind of sorted out how to do it, and there we're able to do it. Other kinds of things. Well, let's look at this. So let's say you do an integral here. So there's a standard integral. We can do it. It comes out in terms of whatever it is, arc cotangents and so on. But let's say you're doing this in more sort of college level math type thing. What you might want to do is to manipulate the integral before it has been done. So we have this general mechanism, inactive, which is a general mechanism where you can wrap the head of something in inactive, and it will be, for many purposes, the thing, but it won't actually evaluate. Okay, so that allows us, by dealing with these inactive things, we can start doing things like, let's change variables in an integral on the inactive integral. So now we're doing, I remember these things. I started using computers to do these things way too early. So I don't think, I'm not sure. This is a trigonometric substitution, yes. This is the thing one learns to do by hand. And here we can now do that programmatically with this integrate change variables mechanism. Just a useful thing, particularly for education purposes. Okay, the other end of calculus, perhaps, fractional differentiation. That's not currently in sort of the calculus that gets taught. This is the half derivative of x squared. By the way, if you differentiate that again, if you take the half derivative of that result, you indeed get 2x. So this is we're introducing fractional differentiation, which has found a bunch of uses in physics and elsewhere. Okay, completely different direction. One of the things that we've been doing over the course of time, one of the big applications of calculus is the ODEs that represent mechanical, electrical, engineering systems, to do systems engineering and so on. And so one of the things we've been doing, we've been steadily integrating our system modeler system and its capabilities into Wolfram language. System modeler remains sort of the authoring environment for the giant 10,000 element mechanical system you want to create, but you can then sort of play the results of that in Wolfram language. So here's a camera stabilizer. Let's look at what that thing is like. What is it? It's something with a bunch of components. Hopefully it will come to life here. Spinning it, spinning it, spinning. Maybe it's a very complicated camera stabilizer. But in any case, there we go. So this is a collection of components. These components are things you find in the Mathematica library, and you put them together. And now one of the things we've added is this concept of system measurement. So we've been able to simulate these systems, produce graphics and so on. Here, there's the question of what are some key parameters of this system as an engineering system. And so this will now do a simulation and start getting results for, I don't know what these are, max overshoot percentage and so on. These are sort of parameters of the system as an engineering system deduced from this kind of symbolic representation of the system. And by the way, as you may know, you could take this system and I could disgorge all the differential algebraic equations, the giant system of differential equations that represents the system. That's what's happening inside. That's what's happening underneath, is the solving of those equations to work out these engineering parameters. Okay, so that's a big sort of festival of ordinary differential equations. Another thing that we've been building for the last 20 years is the ability to do serious partial differential equations. And I think we're now at a very good sort of industrial strength point in terms of being able to deal with partial differential equations. One of the things we've added in the last few versions is kind of a modeling language for partial differential equations, where instead of writing just your raw equation in there, you're doing things where you're specifying things in terms of sort of physically defined objects, like a PDE, a diffusion PDE term. Here's a more complicated case. I don't know how long this will take to run, but this is a heat transport problem where, by the way, you can use sort of real thermal conductivities from our materials database, things like that. Okay, there we go. So this is solving using finite element methods to what's important about this is kind of the setup of the problem in terms of, that whatever that is, that's a Dirichlet condition there that you can state in terms of temperatures and values and so on, having this whole symbolic language for defining partial differential equation systems, and then having the sort of underlying sort of raw material to be able to solve them. This is the thing we've been building to for a long time, and it's really very much arriving at this point. And there are these different areas. These are complicated areas. So in fact, one thing we've been doing is to write what will turn into actual books about all these different areas of PDE modeling. So this was one that just got introduced about hyperelasticity. I was excited because we just introduced this, and I happened to be visiting a company that is in the biomedical space, and mentioning these things, and I was talking about hyperelasticity, and it's like, this is exactly what we need. So that was very encouraging to me. But this is modeling of solid mechanics and so on. Here we've got this very extensive treatment because these fields are complicated. And if you're actually going to do solid mechanics modeling, you have to dive pretty deep into how solids actually work to understand what to do. And we're trying to provide that kind of material in addition to the actual capability to do the computations. By the way, I should explain that everything in all of these documents, it's all click to copy. So you click it, and this is a general thing that we've been doing a lot. You click it, you copy it, you paste it in, then you can just run it. Okay, so let me mention another thing here. So one thing you guys will probably know, this is the root guide page. This is the sort of summarizing all the different areas in Wolfram language. Now there's an interesting little icon that shows up, except that icon just disappeared because I made the window too narrow. There we go. There's a new little icon there that has a person on it. You press that icon, you'll get a thing that says new custom guide page. So what this does, if you've got your favorite functions, maybe you wrote them yourself, maybe you deployed them in the function repository, whatever else, this allows you to imitate the kind of guide pages that we've created for documenting the system. You can create your own guide page, and then all your custom guide pages will show up actually they'll show up, I guess, at the top of your root guide page, and you'll be able to also access them in the cloud and so on. So a convenient mechanism for kind of organizing your own work. Okay, I'm really jumping around here. This is terrible, but I've just something completely different again. Now for something, this is something where the idea of drop shadowing, an effect, along with the effects that we have for cross-hatching and stippling and various kinds of shading, the things that you need. One of the things that I always found strange is that if you look at books about, let's say, mathematical tables from the early 1900s, one of the things you'll find is these very nice hand-drawn, these drawn pictures, and they often use cross-hatching to indicate things. We didn't have that until recently. We now have very nice cross-hatching that you can use as a way to sort of annotate instead of color or something in a graphic. This is just another one of those capabilities. This is drop shadowing. And so, for example, you might use drop shadowing. You've got something here where we draw a plot and we want to emphasize one of the lines, and we drop shadow that line. Okay. Another thing that came in version 13.1, this is a long requested feature. So let's make a bunch of random points in 3D. Let's make some graphics. We'll show where the points are. Okay, people have long said, make me a 3D Voronoi diagram of those points. Okay, so finally, here we go, a 3D Voronoi. I don't know whether people are excited about that here, but people have been requesting that for a very, very, very long time. It turns out to be really hard. It turns out that's why we didn't have it for a long time. It's because it's really hard to get this right and to get all the pieces to fit together. So, I can take this 3D Voronoi, I could just show it in with opacity. There it is. We can see all those little pieces there. Now we can, let's take apart our 3D Voronoi. Let's make it a, oops. It's going to take it apart. Yeah, there we go. Let's take it apart. Here are the puzzle pieces that have to perfectly fit together to make that 3D Voronoi object. And that's the, okay, so now it works. Good. Hey, great. Yeah. All right. Took more than a decade, so we're glad it worked out. Okay, talking of geometry is another thing. Let's say you have a bunch of points. So random points samples points from something. So this will sample 500 points from an annulus. Let's say that you've got those points, and well, okay, we can make graphics for those points here, and it's just they're sort of roughly in the shape of an annulus. Can we reconstruct the annulus from those points? Okay, so we've had a variety of functions, but this is kind of a super function for doing reconstructions. This says make the reconstruction mesh from those points, and it will try and do the best job it can at sort of reconstructing the solid object, and it can do it in any number of dimensions, all those kinds of things, from that collection of points. Okay, another topic. Let's talk about chemistry. So we've, as people may know, we've been building out kind of chemistry capabilities. Think about it, I'd never been a big enthusiast of chemistry, actually, I have to say, but until recently, because chemistry is just this beautiful application of, sort of graph theory meets. It's a wonderful field, and I've been very motivated by seeing how chemistry has worked in Wolfram language to really think about how we can make practical molecular computers, and actually made quite a bit of progress on that recently. But let me show you something here, which is sort of chemistry meets language design. This is a pattern for molecules. And so this is saying a molecule pattern that's a molecule that has sort of wildcard pieces. It has blanks in it. And this says, and this is kind of like how a chemical reaction can be thought about, or like a name reaction of some kind, where you'd say these two, this molecule and this molecule go to this molecule and this molecule, and this is telling us kind of where that. So this is a pattern reaction, and what I thought I might have here, I don't seem to have that. Oh well, I was going to apply that pattern to a molecule, but I seem to have lost my molecule here. So oh well. I might be able to make something up. Anybody know the name of a molecule I can put in that I can apply this reaction to?
Caffeine.
What's that?
Caffeine.
Will it work? Okay, we'll try it. All right, let's see. There is, okay, that should be the caffeine molecule, and we can actually just to show how this works, just to show the structure here, we can just say molecule of that, and this will be then a molecule. You can see it there, and we could say molecule plot 3D of that, and there's our caffeine molecule. Okay, let's live dangerously and try and apply. This should be reaction. Is it? It's chemical reaction apply. Is that right? Molecule. What is the? Anybody? Thank you. Yes. Okay. Apply reaction, and what's that? And then the reaction. Okay. So here's our reaction, and then I want to apply that. This really going to do something? Okay. What are the two reactions? I've only got one reactant. Do I have two Yeah. You see, you've got to have these. Okay. Let's just see what happens if I put two caffeine molecules in there. These chemists, they know what's going on.
So you wanted the reactive molecule. Yeah.
Okay, acetic acid and ethanol. You see, this is all the stuff okay, let's just try this. Acetic acid, there we go, and ethanol. No, there we go. I got the result. So that, yeah, look, there's water there. You can see it did something. So this is like, okay, there we go. So it's, you see, this is what I mean by trying to make the world computable. is, we just put in molecules, we do pattern matching, we get out other molecules. This is a neat thing. Okay, what's that? Yeah, right. This molecule, yeah, right. Water doesn't make it, but okay. So I've showed you a few things which are mostly 13.1 kinds of things. Let me now turn to the as yet unreleased version 13.2. I would say that the lots of things in 13.2. Here's a thing which is a surprise to me. So we've had algebra in Wolfram language for 34 years. Things like polynomial manipulation, things like that. We've been, they work pretty fast and so on. Turns out in version 13.2, polynomial algebra, much polynomial algebra got 10, maybe even 100 times faster. How'd that happen? Well, it's partly new algorithms. It's also because we now have multi-threading and all kinds of hardware capabilities, which we can now take advantage of. So even something as very old line as algebra got maybe 10 times faster. So that's an exciting thing. And usually when you get these orders of magnitude increases in speed, it kind of changes a bit qualitatively what kinds of things you can do. So that means that more things than we could manipulate symbolically before now become possible. So, okay, let me go turn to a different area. Let's talk about something. So we've added in computing. One of the things that's coming in that's happened in the last couple of versions is we make lots of maps. And one of the issues is exactly how are those maps constructed. Are those maps constructed as bitmaps? Are those maps constructed with vector elements where you're actually doing things at full resolution? We are working towards having everything at full resolution. What was added in 13.1, I guess, but made much faster in 13.2 is the ability to have all the labels done with actual fonts at full vector resolution. And we're gradually working towards having all of the backgrounds for geo things done that way. Okay, so that's geo. And geo is already mathematically complicated, and there's all kinds of geodesy. I think we have the best mathematical geodesy capabilities that anybody's ever put together, and we've had this very integrated ability to deal with real-world data in the geographic area, together with these computations, not just for the Earth but for other bodies and so on. Okay, so that brings us to, it's always some. Actually, I'm curious now. I'm just going to do a random thing, but if we say something like Apollo landing sites, we should be able to. Let's just see. I don't know. Let's see what happens if we say geo position of that. Is that going to work? We'll find out. No, there we go. Okay. So if we say geographics or geolist plot of that, that should give us the moon. Okay, there we go. And we can, do different projections on the moon and all those kinds of things. Okay, so we've got on the surface of astronomical bodies, but now we want to actually go for astronomy. Astronomy was obviously an early driver back in Babylonian times, and through the 1700s, 1800s, was a big driver of the exact sciences. And so it's only fitting that eventually we get to making astronomy computational. So what we're building, the first pieces of it are in version 13.2, some of them quite experimental, is the most computational version of astronomy that one's ever seen. So astronomy is kind of complicated. So this is Betelgeuse, a star. This is its astral position, the analog of geoposition. Notice that it says frame horizon. So that's saying what reference frame are we using to describe where Betelgeuse is? That's some equatorial frame. This is a frame. This is flame relative to the ecliptic, relative to the orbit of the Earth around the Sun, and so on. Okay, so we can then say something like, let's plot the astral position of Betelgeuse as a function of time through the course of the day. We can then, and one of the things we're doing here is we have ephemerides. Back from they're a lot better than Ptolemy's ephemerides. Which tell us the positions of things. So here, for example, this is the position of the moon relative to the horizon as a function of time over the course of, I guess, 60 days. Or we could, for example, say, let's look at the position of Mars. Let's see, what does this do? That's the position of Mars. And now we could say the analog of geographics is astrographics, and that's showing them the retrograde motion of Mars as viewed from the Earth, and so on. Now, this stuff is really complicated because you have to start thinking about it's complicated enough projecting things onto the Earth, which is an ellipsoid roughly, et cetera, et cetera, et cetera. But here, not only are we dealing with that, we also actually get to do relativity. It actually matters what the what the times are for different kinds of things. Getting all of that right is non-trivial. So it becomes important to ask the question: what is this? This is the analog of astro distance. This is the astro separation between Jupiter and Saturn over the course of 40 years there. What we end up having to do is well, there's a whole notion of you are an observer here and you are observing something. The light left the thing you were observing at a certain time. You will receive it at a different time. What does it, what time do you refer to? Is it the time when you receive it? Is it the time when the light left the thing? How does that work? It becomes a quite complicated story. You have these light rays and they're intersecting with where you are and so on. Anyway, we're getting all of this stuff right. And this will be, some of it people don't care about yet, although obviously just in these years, this is a time when sort of both commercial space exploration and a bunch of new astronomical data is kind of starting to stream in. And I think this is sort of the moment when it's important to do this. Okay, different topic, machine learning. Something we've done in version 13.2 is the following thing. So neural nets, I would say that the neural nets are becoming more and more complicated, more and more black boxy, more and more difficult to train and build and so on. And we have our neural net repository, which has lots of neural nets in it. But neural nets have increasing tweaking. They're working in different kinds of frameworks and so on. What we've added in version 13.2 is the notion of a net external object. This is a network which is, at first, it will be for the framework for the ONNX sort of cross-framework framework. But it will be for a sequence of different kind of machine learning frameworks. In fact, we hope all of them in the end. One will be able to take a network and just import it into the system as a net external object, and then use that network as something that just operates within the system. So this is now a kind of completely alien network, but we've defined a net encoder that takes images. It's a little bit tricky to do that, but this is very straightforward compared to the things one would otherwise imagine having to do. And now we can run that pipeline of the encoder, the classifier, the decoder. That's just composing those functions, applying them to these images, and now we can use this external network that we imported in here. This particular thing is, I guess, an 8-bit per number, a quantized image identification network. And there are all kinds of things that will come from this. Something is coming sort of the other way around of creating standalone neural nets. Maybe we'll talk about that a little bit more later. Okay, another thing that we've added in recent versions is the concept of biosequences. So a biosequence is a genetic sequence or a peptide amino acid sequence. So this is just a feature of this, a circular peptide with some additional bonds in it now being visualized. We could take, let's take this, and we could take, what is this? This is 2 peptides that have bonds between them, and this is now rendering them as a molecule. So there is our pair of peptides joined together. One of the things that we're building out a lot of capability in the molecular biology type space. One thing that is always a place, sort of a degree of freedom that we now have with our function repository, we're putting sort of preliminary versions of things in there as we develop different kinds of capabilities. So you might find a whatever this is. I'm not sure what this is actually. I don't even know what that is. It's probably hydrophilic, hydrophobic, perhaps regions on a protein. I'm not sure. Here's an example. This is the beginnings of ribbon plots. Okay, so that downloaded a description of a protein, and now this is hopefully going to make one of these nice sort of ribbon plots that's a convenient way to show, you know, the alpha helices and beta sheets and so on in the protein. What's it doing? I noticed something where it said 1 megabyte downloading, so I don't know what happened here. Wake up. I don't know what this is doing. All right, let me give up on that. Sorry. Maybe there's a smaller protein. Anybody know? Okay, we got to help. What is it? 1. Like this? Okay, you were right. Always good to have experts in the audience. Okay. Okay. Let's turn to a very different story. So one of the things we want to do is to make Wolfram language as easy to write as possible. We did not compute its structure. We're actually working actively on that, because now that there are pretty successful, you know, I mean, the pipelines that drive things like AlphaFold and so on, a big part of that is multiple sequence alignment. And the unspoken thing is there's a terabyte of data that you need to compare your original, the sequence you're trying to, the protein you're trying to fold, you have to compare it with a terabyte of existing data. Then you get to do some machine learning stuff. And so what we're trying to figure out right now is how to kind of, not everybody wants to download that terabyte before they do their sort of preliminary folding of things. And so we're trying to get something where there's sort of a preliminary folding that can be done with lower fidelity with a much smaller machine learning system. And then, we have this pattern of performance goal arrow speed or performance goal arrow quality. Performance goal arrow speed will give you an approximate folding. Performance goal arrow quality will say you're now about to download a terabyte of data. At least that's the current idea. That will let you do much more accurate stuff right on your computer. So okay, I was saying, kind of one of the stories is, how do we make Wolfram language as easy to write as possible? And one of the things that there are different dimensions to that. So one dimension to that is, which actually I was going to talk about later, but is Wolfram Alpha Notebook Edition, where we're using the natural language understanding of Wolfram Alpha to be able to do a zero documentation way of getting access to Wolfram language capabilities. Okay, but another thing we want to do is, you're writing code, and we provided syntax coloring, we provided an increasing, we're gradually, like in a recent version, we have it so that the brackets close automatically when you first type them, things like this. We just changed, actually, the coloring. It's now yellow, bright yellow here, because it was, I thought at least, it was very obscure what the yellow and so on meant. And so now we've kind of made it so it's more obvious what things are matching with what and how they get colored. These are all things which you barely notice, but they just help guide you to write correct code. So here's a scenario that comes up. So we have, let's see, what are we doing here? We need to, I think I need to open another notebook here. Yeah, there we go. Okay, so all right, let's see if this works. Let me enter a piece of code. Looks okay. Well, actually, it isn't okay. Actually, it's generated a bunch of errors. Okay, so what we've had here is this dot, which allows us to go and dig in a bit to what the error is. What we're trying to do is to make a collection of code tools that allow you to analyze what happened and see how to fix it. So here we've got a little button that says Analyze Input for Issues. So I press that button, and now it'll start doing the whole analysis, and it will say, and I guess this doesn't magnify with the with the magnification of the notebook, but it says code analysis, and it says use M vertical bar in alternatives N elements of integers to specify assumptions for multiple variables. So we missed a parenthesis here. But the whole point was that we're kind of triggering this code analysis. You get to trigger the code analysis if a message got generated. There's probably a sign that something went wrong. And so now this allows you to go back and do more detailed code analysis, kind of linting of your code to see what might have gone wrong. And this is the thing we're building out more and more with rules-based things and some machine learning-based stuff, although I think the rules are currently winning in terms of what's being most useful, in terms of being, and increasingly also we'll be doing type analysis from courtesy of our whole compiler project to be able to see more about sort of what might have gone wrong with the code you wrote and give you suggestions about how to make it better. Now, this is part of this code assistance thing is you've typed a piece of code. We know it has a very high probability of being wrong. We can tell you that, and we can give you a suggestion about how to make it better. Well, it's not definitively wrong, but it has a very high probability of being wrong. It's kind of like spell checking. It's kind of like a semantic version of spell checking. So that's one thing. Another thing we're working on is is kind of error handling and so on. So when you write a piece of code, you usually are just thinking about what's going to happen when the code works correctly. The issue is there's this kind of subterranean story of what happens when the code didn't work correctly. And you usually don't want to spend a huge amount of time thinking about all of those sort of error cases and all that kind of thing. Our goal is to try and automate as much as possible the safety net of what happens when the code didn't do the right thing. And there's no universal answer because, let's say you generate a message and it's got some convergence error in some numerical thing. It might be, well, I don't really care about that. It's okay. I'm just doing some approximate thing. It might be you're about to launch some spacecraft and it really matters whether it is pointed this way or that way. And then you want to stop if the thing had any kind of error. So it's very much in the eye of the programmer, but what we're trying to do is to kind of curate and characterize sort of different error paths so that we can automate as much as possible, essentially the secondary code path of what happens if the code doesn't do what you expected it to do. So that's a project we've been working on for a while here. The kind of confirm and close framework was the beginning of kind of being able to, in a more modular way, understand how to deal with errors and so on. Another thing that's coming, just mentioned, not really ready yet, not ready to demo, not in version 13.2, unfortunately, is percent modernization. So I use Wolfram language every day. I write tons of notebooks. I can be kind of lazy and I'll just write percent, as a use the last output. And so I get these notebooks which have long threads of percent, percent, percent. Then I want to rerun the thing and it's like, this doesn't work. It's very frustrating. So we have a big project to do percent modernization, where what's going to be happening is when you type a percent sign, there will be an autocomplete that comes up that allows you to choose whether you actually want to burn into that percent the actual expression that was there, the position in the notebook that was there, et cetera. So it's a way of making it so that, it's as convenient as using percent, but it kind of helps you to not make something that is non-portable. So another big story of many years now, but really coming to a very important point is the compiler. So we've been building kind of a new generation compiler that compiles Wolfram language code down to LLVM and essentially directly to assembly language. It produces incredibly efficient code, and it's a very complicated piece of technology to create to take our very high level symbolic language and to compile it. What does it really involve in compiling it? I mean, part of the story is that one is kind of taking the low-level we have a very high-level representation of things, but often there is a way to specialize that. Oh, we know it's going to be a machine integer. It's going to fit in a machine integer, so we can efficiently implement it as a machine integer. So let's do that. Now, the compiler is a big project, which has, as I say, been going for many years. It has various little pieces that have been emerging. So one example is the data structure project, where we have all sorts of standard, people who teach computer science courses should absolutely be using this, because it's, all the linked lists and all this kind of thing. We have that in a nice symbolic form, and it has automatic visualization, and you can do all of those kinds of operations. So we gradually add data structures to, let's make one here. Let's say this is a KD tree, standard kind of computer sciencey data structure. There it is. Well, there's the structure that was being made. We can always ask for sort of a graphics representation of this. Here it is. But now this is a completely sort of down to the metal KD tree that is implemented through our compiler, and that you can use as an element in a kind of down to the metal type algorithm. And for us, one of the practical things is this. A lot of Wolfram language is written in Wolfram language itself, but the core kernel of the system, which we started building in 1986, is written in an extension of C. And so the goal has been, we don't want to write any more C code. We want to write everything in Wolfram language, but in order to achieve the same level of efficiency that's right down to the metal for certain kinds of things, we need to give it we need to have these low-level data structures. We need to have the ability to compile things down. So there's sort of as I say, a big story with many different pieces coming out. So one thing that's happened in, let's see, in compiler land is a thing called the expr struct. So normally when you have an expression in Wolfram language, the evaluator is going to get its hands on that expression. It's going to try and evaluate and get an answer from that expression. Sometimes you want to hold the expression, or we have hold for doing that. You want to inactivate it. We have inactivate for that. Sometimes you just want the raw tree structured thing without any possibility of evaluation. And you can now do that with the expr struct data structure. So I just read in a file with a bunch of these expressions, which are now pure syntactic objects that are just symbolic things that have no possibility of evaluation. They're as dead as there's dead as an integer or something. But now we can do operations. We can say select those expressions which have a head that is set delayed. So this is a way that we can manipulate, for doing certain kinds of metaprogramming. This is a convenient thing. Actually, we have more coming along these lines. We have a kind of code tree structure that's coming, which will be an even more sort of streamlined top-level version of an abstract syntax tree, actually, a syntax tree, sometimes abstract, sometimes more concrete. Okay, so another thing that's part of the compiler that's been arriving recently is the ability to use the compiler as a way to link link in external libraries. Okay, so this is a little bit obscure because we're dealing, we're hacking into the jungle here, because this is an external library written in C. This happens to be a function from the OpenSSL library, and what this is doing is this is a translation of the rand bytes is declared in the C program as an unsigned char star and an int. Okay, so here it is. This is the Wolfram language representation of an unsigned char star. And this thing, by the way, this colon brackets, for those who kind of pay attention to the extension of Wolfram language syntax, that is a syntactic form for a type specifier. It's just we finally gave up on having to type the whole type specifier word, and we actually have a syntax for that because it's something that arises all the time when you're creating compilable code like this. Okay, so this is going to make a declaration, just a symbolic declaration of this rand bytes function, which is a C function. This is its signature in C, and now we can say, in here we can say let's actually make. So this is the complete code that connects the C library into Wolfram language. And so this is saying create a type instance. This is a managed. That managed thing has to do with memory management, a very tricky thing to deal with when you're dealing with external libraries. This now creates a type instance in numeric array, et cetera, et cetera, et cetera. So let's run this, and this should do the linking of that external library. And then once we've got this, we should be able to run, okay, there's the compiled code. Let's just take that, we called it CF there. Let's just take that, run it on, let's say 10 elements. We get a numeric array. If we wanted to, we could just ask for the normal of that, and we get a bunch of bytes. Okay, so this may not, I don't know, to some people this might be impressive. This is impressive because it is actually very non-trivial to link an external, you know, from the wild C library directly into our language. And what used to take, you know, a week now takes 10 minutes or something. So this is real progress in doing this, and this allows us to really and everybody to really ingest things from the outside world, bring them into the language. Now, by the way, the Paclet mechanism that I'll talk about a little bit later allows you to take something like a library function like this and put it in the function repository, directly just use it as a thing that looks, as far as one's concerned, as just a standard piece of Wolfram language code. But it happens to, underneath it, it's rooted in this external library. Okay, so we're kind of, the goal is to sort of knit compilation into everything. So let's see, what is this? What is this? Okay, let's just define some function here. And I'll just define a random function. And now, okay, so when you write, okay, and now let's do this. I'll explain what I'm doing in a moment. So you write compilable code. What you're doing when you write compilable code is you're giving certain clues. You're saying this is a type integer 64. Usually in using Wolfram language, you absolutely don't care that it's integer 64. That's completely automated away. You don't need to know that. You never need to touch it. But if you're trying to make something which is right down to the metal, you potentially need to say, I only care about integer 64 here. Okay, so one of the things you can do is there's mostly these things where you've specified right down to the metal how you want it to work, but sometimes you need to call back into the evaluator, and there's the kernel function mechanism for calling a function back into the main kernel in the main evaluator. This is another mechanism. This is a down values function. So I defined these down values for the fun function. And then what happened here was I did a function compile, and I specified a down values function of fun, and this thing chased down through those down values to compile all those down values. And now if I say that function of 10, it'll go and use those down values to give me the value 1. Okay, so this is again, it may look like detail, but it's really very important because it means you can have this big chunk of code defined in standard ways with down values, and then you can access that code and you can compile it as a piece of sort of down to the metal capability. Other kinds of things coming in 13.2. This is just a function that lets you put into code. This is part of the sort of story of knitting compilation into everything. So this thing, you can have a lump of code which, if it is run in the compiler, will work in one way with type checking and so on. If it's run outside the compiler, it'll work in a different way. So that's when you deal with this type calculus here, and we have elaborate type calculi, this thing is just an inert type specification. But sometimes you want code where you're just giving a type hint. So here, this is a function with a type hint. And that type hint is something which, if you run the code in the evaluator, the type hint will evaporate. But the type hint, if you fed this code to the compiler will say, thank you for that hint. I'm going to use that type hint to be able to set things up. You know, I was just kind of interested to see, if you look at the sort of long arc of history of things, I was looking recently, see if we can bring this up. Here we go. It's kind of funny. This is part of the SMP documentation from 1980, 1981 maybe. And it's talking about the function cons. SMP had these stupid short command names and so on, recently unbundled into these other functions. This was the compiler of SMP that would take SMP functions and compile them and load them and so on. Well, we've finally been able to really do much better than this. And although it's taken 40-something years, and this is, you know, the stack of software engineering necessary to make this work is a tall one. Okay, talking of making new stuff work, here's another new area, which is our quantum framework. So a lot of people have used Wolfram language to think about quantum mechanics and quantum computing for a long time. We decided to try and start making something which is sort of a standardized representation for quantum computing. Now, I have to say, our physics project has taught us a lot about how quantum mechanics works. My friend Dick Feynman always used to say, nobody understands quantum mechanics, even though he'd spent his whole life working on quantum mechanics. I think we are now, thanks to our physics project, very much at the point where we can start to say, we finally understand quantum mechanics. And that tells us a lot of things about quantum computing, but the formalism of quantum computing, independent of its practical implementation, which has a bunch of issues, which I can talk about separately, but the formalism is very interesting, and you'll see that show up in a bunch of other places in our system. And the formalism is now something that we're trying to build a good standardized way of dealing with. So there's a quantum circuit operator. We can apply this quantum, oops, I got rid of that. This is applying the quantum circuit operator to an actual state. In traditional form, we get those nice little kets there. This shows us symbolically the superposition of those two states. We can go ahead and say, let's create an actual, this is a quantum circuit here. Oops, this is, I need to make it bigger because otherwise all those things collide. That's a quantum circuit. And we could, for example, take that quantum circuit and what are we doing here? We can turn that into, for example, a tensor network. There it is. We can do all sorts of operations on it. This is now something which brings kind of quantum computing very much into our kind of domain of operations. And you'll see, maybe I'll talk a little bit more about how our physics project, how this relates to sort of more general understanding of related kind of concepts of category theory, et cetera, through our physics project. All right, another area, blockchain. We've been continuing to do lots of stuff with blockchain, particularly working with the Cardano blockchain in the past year on many projects. Last year we did this distributed consensus conference, and we'll be doing another one of those in the slightly more general conference coming up soon about in this blockchain area. Other things I should mention here. This is something in the import-export area. We're having this standardized element for import-export. We have, 400 or 500 different formats now that we can import and export. This is a standardized way of just getting a summary of what's in a file. This is, in this case, a TIFF. Okay, more and more formats getting added. This is a chess format. And so here we've got this imports as a chessboard, and we can do all sorts of things with that. That's another kind of thing. We also have, let's see, I'm not sure I have an example of this, micro QR code support. Let's see, what else do we have here? We have, here's an example of something else. So one of the things we added is this notion of a form notebook. So we have the notion of forms where you're filling out, you have a bunch of input fields, you're filling them out. But what if you want to fill out a more complicated form? Something which maybe has the structure of a notebook, but where there are quotes fields in there, which are just cells in the notebook. Now, normally what you might do is you'd say, well, write this notebook, and then we're going to scrape the notebook for the data we want. We're trying to have this notion of a form notebook where you can create a notebook which is kind of already defines. So for example, if I go here, programmatic notebook, form notebook authoring, this is now allowing me to author a form notebook. And it has all sorts of different things. I can insert a form element, what kind of form element, a radio button, this kind of thing. And then from this, I can generate something which will then be sort of an active version of this form notebook where somebody can fill out the form, press submit, and then that will automatically through the cloud or elsewhere be the sort of the content of that form will be extracted and returned as a piece of computable data, perhaps an association. Okay, so building on that framework, we also then have the question framework, which is a thing where you can think of it. One of its use cases is writing quizzes for education. This is now an example of a quiz notebook that was specified where we have these question objects, which are specifying a question interface. It's got an answer, it's got a prompt, it's got various kinds of things that can be there. et cetera, et cetera, et cetera. So this is a programmatic specification of a quiz together with its assessment mechanisms. Okay, so we can now say here, generate, and this will, what is this going to do? It's going to deploy this to the cloud, but how am I going to know where it went? Oh, there it is. That's how I know where it went. It actually just made a notebook, which I can now, question index, what is this? Oh my, opening cloud, okay, thank you. So this is now a version of that. I created this collection of questions that will now be where hopefully this form will come up that allows me to fill in, to answer the quiz, press done, and have it. Here we go. Okay, so it created this quiz, and now I can start filling in entries, results from this quiz, and I can pick I can pick whether I want sort of immediate feedback on what I'm doing, or whether I want to wait until the whole quiz has been done. I can pick whether I want it to be a very secure thing where nobody could possibly cheat by having the answers, extractable because they're on some server somewhere, et cetera, et cetera, et cetera. But so this is a way, I think this is a pretty powerful technology for people, for example, in education or in areas where you need to collect data, doing surveys, things like that, to be able to get sort of computable access to that kind of data. Okay, quite different thing I'll mention here. Oh, what's this? This is the quiz, I guess, has been deployed. There it is. Okay, let me talk about something completely different. Let's talk about very foundational things in Wolfram language. Okay, when I first developed SMP forerunner to Mathematica and Wolfram language, it was from the beginning an infinite evaluation system. You put in an input, and the goal of the system was keep grinding until you get an answer that doesn't change anymore. And people said, who were sort of knowledgeable computer scientists, they said, this system could never work. It's impossible. It's theoretically impossible. What happens if you type x equals x plus 1? Because it's an infinite evaluation system, so what's it going to do? Well, turns out that that particular limit is not one that people run into very often. Any system that has an evaluator has weird cases. And this is the weird case that you get. Now, one thing we've done now is we're starting sort of a more of a calculus of what happens when you run into those limits. So there's this notion of a terminated evaluation that actually will later on it will store pieces of essentially the structure that got you to that. Now, another thing that will be maybe coming in later is in connection with infinite lists and other infinite structures. It'll be the first use that I'll have made in my life in practice of transfinite numbers will be for describing these kind of infinite data structures that you get from things like x equals x plus 1. Let's get rid of the value of x here. Now, this is part of a much bigger story. Let me mention this. I suppose I'll mention this now. Okay, so let's see. Well, one of the things that's come out of the physics project is this notion of multiway systems and the importance of what we call multicomputation. So here's a typical example of a multiway system. This is a string rewriting system which has rules A goes to BBB, BB goes to A. What is a multiway system? A multiway system is just something where at every step you're following all possible rewrites. We're doing all possible operations that are specified by these rules. So in this case, A just goes to BBB, but BBB, there are two things you can do, because BB, it could be the first BB that goes to A, or it could be the second one that goes to A, and they give different results. Okay, so these multiway systems are, and I can describe this in much more detail, but these multiway systems are what's underneath quantum mechanics. And they're in fact, it gets very brain twisting because in the end, we are observers of these multiway systems, and we are multiway systems ourselves. And so sort of the story of quantum mechanics becomes this strange story of how does a branching brain perceive a branching universe? Let's put that on the side. Let's just talk about multiway systems. Multiway systems are a very sort of a way of thinking about sort of a new level of computation. So normally in computation, one has this idea of sort of single-way computation. You're doing an evaluation, you're keeping on grinding, and eventually you go from a question, grind, and then you get to an answer. It's a sort of single thread of experience, single thread of computation. In a multi-way system, that's not what's happening. You're instead following all these different paths of history. And you're bringing, and what's happening is there are equivalences between the results you get from different paths. You're bringing those together. This whole thing is defining sort of all possible non-deterministic paths you might follow. So in typical non-deterministic computation, like in NP or something like that, what you're interested in is, if I try all these different paths, is there a winner somewhere? Is there a result which I can verify in polynomial time, et cetera, et cetera, et cetera? You're following a single path. So in this case, we're not, in multi-way systems, we're following all paths. And the question is to sort of make a sort of a way of thinking about science in terms of following all paths. And it's turning out that multi-computation is a very critical sort of core element of physics, mathematics, I think molecular biology, biological evolution, maybe economics, maybe a bunch of other areas. It's kind of, I mentioned these sort of three epochs of the development of science, from structural to mathematical to computational. The multi-computation one is the next one, I think, and it's one that we're just starting to see now. But so one of the things which is a challenge for me right now is, can we understand how to make multi-computation a core element of Wolfram language? And what kinds of things can we think about in terms of multi-computation? So for example, you could think about, I don't know, if you make it a game graph. I had a post about this a little while ago, the game graph of tic-tac-toe. That is a multi-way graph. It has, from every state of the game, you have multiple possible moves you can make, and you can make statements about this whole multi-way graph that you get from the game. But there are a huge number of problems that end up turning into multi-way graph and multi-computational problems. And the question is, what are the primitives? What are the things that are kind of like the functional programming that we know now? What are those things for multi-computation? Turns out one of the things that's a tricky business in multi-computation is that in single-way computation, there's always just an answer. In multi-computation, what you consider the answer depends on who's looking at it. What observer is sampling this thing? That's something in a big version in our physics project. That's the story of observers sampling this Roolead of an entangled limit of all possible computations. But at a more sort of tame level, there's a question of what are you sampling? So for example, you might want to do probabilistic computation in which you slice across here and just say, what's the probability of reaching each of these outcomes and so on. So, okay, so the question is, so let me say one other thing, which is that when I first built SMP, forerunner of Wolfram language, the whole story was already kind of a story of making transformations on symbolic expressions. And I was very lucky because I kind of had this idea that it would be okay to just do, if you look at all possible transformations that you can do at every step with symbolic expressions, to just take the first transformation that works, just keep doing that until you reach a fixed point. That's how SMP worked. That's how Wolfram language works. Just applies transformations to symbolic expressions until it reaches a fixed point, always picking the first transformation that works. Okay. Now, I was well aware back in the beginning of the 80s, I was well aware that there were many other possible paths you could pick, but I didn't know how to disentangle what paths you should actually use. I tried to parameterize that even in SMP. Nobody, including myself, understood that parameterization very well. That story of that parameterization turns out to be a story equivalent to the story of reference frames and relativity and a bunch of other kinds of ideas. But the basic point is, in sort of single-way computation in Wolfram language, we are picking a particular path through the multi-way system. And it turns out that for the types of computations we've been wanting to do, that works fine to pick that one path. But now the question is, well, what happens if we pick all the paths? How do we make kind of a language design, an understandable language design for that case? Well, let's take a look at some of the things we can start to think about. So this is the thing, this is a trace graph. So this is the beginning of a representation of what actually happens in the evaluator. So what's happening is, this is saying there's 2 times 3, that's 4 times 5, there's 6 times 7. Those are evaluated. They're recombined to 6 plus 20 plus 42, which is then computed to give 68. So that's a simple example of a trace graph. This is a single way computation. One of the things that's tricky is that there are actually two recursions going on. There's a time-like recursion going down these kind of branches in time. This is a time-like process. And there's a space-like process where we're going across the different elements of this expression. And so what the story of our evaluator is a story of time-like evaluation, transformations on things, and space-like sampling of things as we go through a list, or we go down, or we recurse through an expression. So very much like what happens in physics, there's space-like separation of things, there's time-like separation of things. So let's look at a couple of other examples. This is a slightly more complicated trace graph for that little operation there. We'll see the different parts of the do being evaluated and doing their thing. Okay, so now let's do another example. Let's do a Fibonacci sequence, see what its trace graph looks like. So let's define a Fibonacci sequence here, and let's just write it out. Actually, okay. We're just going to, instead of writing fib of something, let's just write fib of something. It's going to be clear what's going on. He says, well, okay, so this is Fibonacci recursion, right, shown as a trace graph. And we can simplify it slightly here by doing that. And so that's the Fibonacci recursion. Maybe we could try a slightly bigger, let's try 8. No, let's try 10. We'll live dangerously. Okay. Okay, so this is recursion. That's what that kind of recursion looks like. There's a mixture of time-like recursion and space-like recursion evaluating Fibonacci function. Okay, so just not to blow things up too much, but there's another kind of separation that isn't time-like, that is something leads to something leads to something. It isn't space-like you sample different elements of a list. It's what we call branch-like. And branch-like separation is what happens a lot in quantum mechanics and so on. Branch-like separation is you picked a different path in the evaluation. You picked a different path in the multiway system. So in this trace graph that's showing, so this, what I'm showing you here is the standard operation of the evaluator. That's the sort of taken apart, space-time decomposed version of the evaluator. But now there's another dimension. There's a branch-like dimension that shows up. And that branch-like dimension is the thing that we're capturing in multicomputation, and that's what we have to understand how to deal with. I mean, just to not be too physicsy about it, but you know, if you're into the ADS-CFT correspondence, the correspondence between space-like and branch-like is the ADS-CFT correspondence, we think. That was so it has.
Sorry. There's a lot of copies of each other, no?
Yes. This is not deduplicated. This is that's a whole different issue, is deduplication, equivalencing. That the story. Okay, so not to get at all deeply into this, but you know, in these multiway graphs, the raw multiway graph is just a tree. It just says do all these different things, and every different thing that happens is just a separate branch on the tree. Question is, and it could be that that's all there is. And in fact, in the universe, my guess is the raw universe looked at in the kind of outside the universe view, it's just a giant tree. And all these different, you know, possibilities are happening in this tree. The point is that we, as observers embedded in that thing, we think that there is a definite thread of experience. And so we equivalence together things which are the same. And it's okay to do that. We can successfully equivalence things which are the same, which is why we can bring these things together. Now, in fact, we do more than just equivalencing things which are, okay, if these things were hypergraphs, as they are in our physics project, rather than strings, equivalence is not so obvious. It's hypergraph isomorphism rather than just literal equivalence. So it's a bit more complicated. And then, in fact, observers like us do much more equivalencing than that. And so this sort of story of what's going on is it's the story of transformations between things. So in a sense, multicomputation adds to the idea of transformation, the idea of equivalencing. And the idea of equivalencing is deeply bound up with the notion of how observers work. And this idea of equivalencing and this observer theory one has to build, this is something we have to build in order to be able to understand how to do multi-computational computation, so to speak. So anyway, that was sorry, that went pretty abstract. But this is to me, it's something, once we can crack this multi-computation idea and bring it into language design, it's going to open up a whole lot of things, because I think there are a lot of areas where multi-computational models are the right kind of thing, but we need to have kind of, just like things like cellular automata, a good raw material for thinking about the computational modeling. So multi-way systems are good raw material for thinking about multi-computational modeling, but we need kind of a way of being able to program with them, and that's what we're trying to build. So, okay, let's and I would say that the whole thing about how quantum circuits work, the whole thing about how tensor networks work, category theory, the monoidal categories, things like this, these all turn out to be the same story. It's similar to if you have a function, you say f of g of x, you've got just a single chain of functions. But if you start having functions with multiple arguments, you have kind of a string diagram of kind of this connects to that and this connects to that and so on. You have these graphs that represent the sort of flow of data. And these are all sort of the same idea, and we're trying to make this part of our language design. So that's my homework for the next quite a while, is trying to untangle that and make it simple enough that we can all actually use it. Okay, so quite a lot of what's happening here is we're introducing a lot of new things, and quite a lot of them show up first in our function repository. And many of you, I hope, will have seen this. We've added, in the last year, we have added 400 new functions to the function repository. Function repository is something which I should emphasize. It's very fast really, really fast, and I've done many of them myself, to create an entry for the function repository. And if I could bring up this notebook, where is it? Where'd it go? There we go. So this is the authoring notebook for the function repository. You author, you just put in the code for your function, you put in some documentation, then you can say deploy, and you can either say locally on this computer for my cloud account, publicly in the cloud, this session only, or you can submit to the repository. One thing that's very convenient in projects that I do with people is everybody deploys these things publicly to the cloud. So that means it's not yet put into our centralized repository, but it's something where you can immediately make use of this function just by calling resource function on this URL that has been put into the cloud. So it's a convenient way to kind of share code, and it's also something where once it's in the cloud, if the person doesn't delete it, that code will continue to work. So many things have been put in the function repository, lots of useful functions. The one feature of these things is this is all click to copy. So you click in there and you can use it here, and it says resource function of that. And oh, look at this. I was going to show this later. This is a mechanism. It's kind of nice mechanism. This is saying there's actually a new version of nest graph tagged, but I'm still going to run it. The system is saying even with the old nest graph tagged. But it took us a while to sort of figure out the UX of this, because you don't want it to just, if you're in the middle of running something, you don't want it to block and say, hey, stop. You've got to decide whether you want to download something. That would be horrible. So this is a thing where it just runs anyway, but it gives you this notifier that says, well, there is actually an update. So if I say update now, there we go. Okay. It'll update that to version 2.0.1, and then it'll say reevaluate that to use it. So it's a mechanism for being able to do updates without getting in your face, so to speak, and making being obnoxious about doing the updates. Now, I will say that there actually now also is documentation. All the previous updates to these functions are now documented. So you can find in the function repository, you can find the documentation for all previous versions. So when you write code and you use function repository functions, or you get other people to write code using them, they can go back and look at that documentation for older versions. And when you decide to use a function, so probably here, if I use this function, this thing, I'm going to guess, it doesn't do that. I thought that would actually, it should do that, is to give is to make this be a little blob that actually burns into itself the fact that that was a previous version of the function. All right. When if it is burnt in. It didn't go well. You updated it. It didn't go that well. Yes, yes, you can. You just say to the resource object that represents that function, you just remove that resource object, and then it will come back in again. In the you know, it'll re-download. Okay, so well, gosh, there's just all kinds of functions that have been added. I mean, there's lots of things for particular areas. I don't know, what is this? Random entity question about, what is this? I don't know. So it's asking me a random question about which country has the capital city of Jakarta. Okay, even I know that. So, okay, and just a lot of specialized functionality has been added to the function repository. That's some kind of plots of pulsar information, etc. In our physics project, we've added lots and lots and lots of functions. And this is the way that this is part of sort of the open research that we're doing on our physics project. You'll see actually here a lot of stuff on category theory that's been added that is part of a big category theory framework for Wolfram language, which connects to all of these other things I've been talking about. Okay, so in addition to the function repository, the whole framework of repositories, we've got neural net repository, we've got data repository, we're adding a bunch of new repositories. There'll be a color palette repository, there'll be a style sheet repository, there'll be a plot theme repository, all these kinds of things. Big repository that has just now gone live is the Paclet repository. So the Paclet repository, let me bring it up. So the Paclet repository is a place where you can put bigger packages, and these packages can include not just Wolfram language code, but library code. They can include documentation. They can deploy new palettes. They can change the menus. They can basically customize the whole system. So packlets are things that we've had for more than a decade now, but we've been gradually making them more accessible to people, more to the point where anybody can write a Paclet. And we've also had private Paclet repositories for a while. This is now a public Paclet repository. Now let me explain the relationship between sort of the Paclet repository and the function repository. The function repository is a one function at a time story. It exposes functionality one function at a time. Very convenient, very modular, etc. The Paclet repository is when you have a big collection of things, like the quantum framework is a good example of a Paclet. And it's a big Paclet. It's got lots of different functions. It's got lots of things in it, and so on. And this is something where these are all interconnected. Now, it turns out, and that's built as a Paclet, and then it has all its documentation here, et cetera, et cetera, et cetera. It's all click to copy. But this is an interconnected large framework that's put in as a Paclet. Okay, so one thing you can also do is and the other point about the Paclet repository is it's not curated. So we're not sort of pushing back and saying, you know, define your function this way, make the thing follow these design principles and so on. The Paclet repository is kind of a Wild West type area. But we hope people will put wonderful things in it. But it means you can deploy something to the Paclet repository and immediately it will be there. Then the other thing is the functions that are in the Paclet repository, you actually can deep link, so to speak, into those using Paclet symbol. Just like in the case of you have resource function, you can get to any of these things by sort of specifying the Paclet path to get to that symbol. So when you've deployed a Paclet, you can give somebody a notebook that references that Paclet, and even if they haven't downloaded that Paclet, if you put in Paclet symbol in the notebook, it will automatically download the Paclet, set things up so that you can use that particular Paclet symbol. Okay, so the Paclet repository is just now going live and gone live, and we really hope at this conference, people will, I think there are 6 different talks and a workshop about the Paclet repository. You know, take the code that you've written perhaps over the last many years and make it into a Paclet, put it in the Paclet repository, because then you'll be able to use it and other people will be able to use it, and it will be a nice streamlined place to have that code. This is a Paclet about multicomputation. That's the place where we're really doing the research work on multicomputation, is being sort of opened up and put in this Paclet as it gets created. Okay, and by the way, when you make a Paclet, one of the things that is an important part of it is the documentation tools that we built, which are kind of a version of the documentation tools that we've had internally for many years. But this is allows you to make a new function page. Oh, I've got to choose a Paclet directory. Okay, this allows you to basically build documentation that's just like the documentation we have. It's a nice streamlined way to do that. That's the way to build a guide page, etc. Okay, so let's talk about deployment mechanisms for a second for our system. One of the things that boy, I thought I didn't have much to talk about, but turns out there's rather a lot. So let's talk about deploying Wolfram language capabilities. So we've got a variety of different mechanisms for deploying Wolfram language. We've obviously got the cloud, the public cloud. We've got Wolfram Engine and the free Wolfram Engine for developers. We've set it up so that you can download the Wolfram Engine from any old Paclet repository. We've been putting it into all these different Paclet repositories. You can get the free Wolfram Engine for developers all over the place and start using it. We've also been setting it up so that IDEs, we have increasingly good interactions with different kinds of IDEs, and the ability in Visual Studio, Visual Code, whatever it's called now, or in Sublime, or whatever you use, to get some of the capabilities of code entry that you have in notebooks. So using LSP, Language Server Protocol, we've got auto completions of symbol names, we've got a bunch of syntax coloring, we've got a bunch of code formatting, etc. That allows one to be using a text editor in an IDE and be dealing with Wolfram language code in a good way. But so that's sort of the Wolfram Engine story. We've got our private version of our public cloud. We've also got our Wolfram Application Server, which is a kind of fully multi-machine, containerized way of deploying Wolfram language APIs and so on on a server. I might say that one principle that we've sort of had as a business and as a technology strategy is we're not going to lock people into using our particular cloud or anything like that. It's not our business model. So anything that you can do in our public cloud, it's convenient sometimes to use our public cloud. Lots of people use it. It's a good thing. But if you want to, you can have your own on-premise version, or you can be running it in a cloud services provider's machines. You can make your own version of anything you can do in the public cloud, you should also be able to do locally. And that's something we're providing through Enterprise Private Cloud and through Wolfram Application Server. And I should say Wolfram Application Server, for example, Wolfram Alpha will soon be running on Wolfram Application Server. It's a very industrial strength containerized version of Wolfram Engine, etc. So, and the whole containerization thing is coming to all of our various system services as a way to help in this deployment, local deployment of everything. Okay, another thing we have, which is kind of neat, I think, is standalone applications. So you have a program written in Wolfram language, and you just want to deploy it as something which people are going to run on a command line. How do you do it? Okay, so what we have, it's not, it'll be coming out in the next few months, is the ability to make a bundle that contains a Wolfram engine together with any specific code that you have. So when you go to that command line, it just runs that particular piece of code in the Wolfram engine. And how big is it? I believe the current smallest size is like 160 megabytes, which is tiny in the modern world. And so that's the thing you staple on to your piece of Wolfram language code, and you make this bundle, and then you can just run it, and you can give it to anybody, and you say, here's this thing, and it runs, and it happens to be using Wolfram language. So that's a way that works, and you can also either run that as a shell command line type program. You can also run it as something which is a dynamic library that can be connected into some other programs. There's all that software engineering that's been done. So for example, our LSP server, the thing that runs IDEs, that runs syntax coloring for IDEs and so on, that is a standalone application created from Wolfram language using the standalone mechanism. Excuse me. So there'll also be a mechanism. So this is the thing where you can make a standalone application, and it's a complete, you pick it up, you run it, it's got the Wolfram engine inside it. We'll also have more like a JRE type model where there is a centralized Wolfram engine that you can call from a bunch of different applications. Same basic mechanism. Okay, so okay, that's a very modern thing that has a lot of modern technology. I just want to mention something which is kind of perhaps a throwback to another era, completely different area. We've been making Euclid computable. Okay, different part of history. You would have thought that in all these years, everything about Euclid would have become computable. It hasn't. We've just been adding in the last few years sort of synthetic geometry primitives to represent and be able to do proofs from Euclid. One of the things we're doing is, this isn't ready yet, but there's this website that, oh look, there's a click to copy piece of Euclid. Euclid won't have had click to copy, this is a thing which represents a bunch of triangles and angles, and it gives a bunch of constraints. And look, there it produced this particular thing that represents a proposition in Euclid. And so we've been curating and making computable, after 2,000 years, what's in Euclid. And actually, along the same lines, the things that were in our geometric scene language, this is, oh look, this actually allows us to also demonstrate cross-hatching and stippling and all that kind of thing. This is just a styled version, again, not seen in this form, I think, by Euclid. It's a presentation of that particular set of geometric constraints and so on. Okay, well, all right. So I've showed you a bunch of capabilities, some new ones, things we've been adding. As I said, one of our real challenges is explaining what on earth we have, because it's a very big thing. We're making the whole world computable, so to speak. There are lots of different pieces. There are lots of different things people can know about. One of the things we've worked very hard on is to make all of this giant computable system, this giant computational language based on a small number of principles. So you only have to learn those principles, and then the rest is just vocabulary, so to speak. You only have to learn a small amount of kind of grammar, then it's all just vocabulary after that. But we still got to tell people what we have. And so one of the things we've been starting to do is to have new mechanisms. That was a bad sign. What happened there? Bad. Okay, let me just try a different way to do that. So we've been starting to have these kind of pages that try and tell you sort of what's the point of geography in Wolfram language, and sort of give you some high-level picture of what we're doing, let's say, in geography. And so we will be adding many more of these pages that kind of give sort of a high-level overview in an easy-to-read form where you can drill down if you want to know more, kind of an outline of what we're doing in these different kinds of areas. Another thing that we have coming is what we call code source. And code source, so we have documentation. Documentation says you know the function you want. Now you can go and understand how to use it. This core areas is you know roughly what kind of thing you want to work on. Here's kind of a big picture version of how Wolfram language relates to that is another problem, which is I've got a specific thing I want to do. I've got this little idea. I want to, write a piece of code that does this. Maybe I've been struggling to do that in some low-level programming language or something. I want to know how to do it in Wolfram language. So our code source pages will be these kind of snippets of how to do things. You can either run them in web forms, you can put them in a notebook, you can deploy them as an API, you can do all sorts of different things. But the basic point is they are kind of snippet level versions of, I just want to do this piece of functionality. Now, we will be opening this up as something that people can contribute to, and we very much would like to get lots of contributions of things, of little sort of snippets of functionality that people want to achieve and that people think other people would like to make use of. So another big story for us is sort of simplifying our product line. One of the issues for us has been, Mathematica was our long-time sort of main brand. We really moved towards Wolfram language as our main brand to describe our sort of broad computational language, because otherwise people think we're stuck in the previous epoch number 2 of my description of kind of the sequence of things for at least science. And we want to make sure that we are explaining that we do more than math. We also want to be able to let Mathematica as such be a thing that can proudly do more and more mathy kinds of things without us worrying, if we tell people we're doing mathy kinds of things, they won't understand that we do a lot of things that nobody would think of as math. Back when I named Mathematica, I actually thought mathematics as a field might progress in a direction that broadened. It didn't. So we're kind of stuck with that reality of history, so to speak. So, but it's confusing because Wolfram language is the language that underlies everything, but it underlies Mathematica, and we've got Wolfram 1 as our combined cloud and desktop system, and so on. We are steadily merging everything into this kind of Wolfram app that will have its different manifestations in Mathematica and other places, and really explaining what it is that we have as this wonderfully unified, wonderfully integrated system that many companies that have complicated software product lines, they would love to have an integrated system, but they actually have 10 different pieces that they got from different places and so on, and they've been trying to glue them together for a quarter of a century or something. But we're not in that position, but we then have to be able to explain to people what it is that we have. So you'll see a number of this is a new Wolfram language homepage that tries to kind of explain in a kind of a quick way sort of what the point of Wolfram language is. Our main page, which will progressively change actually, but this concept of sort of just use Wolfram is a big kind of theme for us, which is you're doing all these complicated things, and actually we have just a solution for that. You can just use our technology and it will work. And so that's kind of the message there, and we'll be reinforcing that in lots of ways. All right, other things. Let's one of the things that we have, which is just a great entry point for our technology stack, is Wolfram Alpha, used by immense number of people and it is a zero documentation story. There isn't any documentation as such for Wolfram language. There are examples, but there's no documentation, and you don't need it. And so it's one of the things that happened recently is Wolfram Alpha got significantly faster. That was the result of a grinding piece of software engineering, which I have to say I was personally more involved in than I would like to have been, but it's interesting because it's like what could possibly go wrong in all of these different different software systems talking to each other and with different kinds of distributed computing issues and so on. But anyway, the bottom line is it got significantly faster, and you will see it get even faster in the coming months as we sort of round out some things that we're doing there. So that's a nice thing. Another thing is we now have Spanish language Wolfram Alpha, okay, it's now I don't think I can type a query in here. That's the bad thing. I think I was given a query here. Okay, here we go. There's a query I can give you. So this is our we have had Japanese also. This is our our second language version. We actually also have a Chinese version, but it's never been deployed. So that's a new thing there. We're actually seeing very nice rapid adoption of the Spanish language Wolfram Alpha, and we'll probably see more of that to come. Okay, another thing that's new in Wolfram Alpha is we've redesigned the Wolfram Alpha app, and I guess I have to show you that. Let's see. Okay, there we go. There's my phone here. All right, so the Wolfram Alpha app, people use it to do things like math homework, and you know, I would say that in the modern world, people want everything to be as easy as possible. So one of the things we made easier is you get to just take a picture. And we can take this and we can like circle that. And we can say, analyze this. And there it is. We can say compute. And there's the result. And we can say, give me a step-by-step solution. And pretty soon, that was pretty easy. That was the math OCR is pretty good. You can take even, I don't know, we can try maybe one more example. I'm going to tempt fate by doing that. Let's open, I've got an older calculus book here. Oh boy, let's see what I can do here. All right, let's do, my gosh, if this works, I'll be very impressed. I picked a page. Okay, let's try this. Let us try, if I can get my finger correctly to, did I miss a piece there? No, I got that. Okay, let's try this. See if I move that up a little bit. Can I move that up? Yes, I can. Okay, and let's get rid of the equal sign, although maybe I don't need to. And let's just try analyzing that. What did it do with the denominator? Help. Or maybe the denominator is there. Compute that. Let's see what happens. Timed out. Try with more time. Maybe this exercise was actually hard. Hey, wait a minute. I think we didn't get quite the right formula because this should have been J, the half integer order Bessel function. But we got pretty close here. This isn't bad. We might have to go and fix the OCR a little bit to get to that actual question. I bet we can do that some. But anyway, it's kind of fun to see how this stuff kind of converges. All right. Another big thing is Wolfram Alpha Notebook Edition. So Wolfram Alpha Notebook Edition is the bridge from Wolfram Alpha to Wolfram language. And so let's see if I can pull it up here. No, where is it? All right, how do I get to Wolfram Alpha Notebook Edition in the cloud? Do we yet have an easy entry point for that? Or do I have to do something absolutely grotesque? Okay, this is the cloud. I'm going to do something. This is what you will not have to do. Okay. This is what we're avoiding you having to do. All right, here we go. So this is Wolfram Alpha Notebook Edition in the cloud, and you'll notice that, and it's something where we can let's see, we can just okay. So you say, what is the integral of x log x, and this is again sort of the zero documentation way of entering things. And here you get the result. You see the Wolfram language result there, and you'll get this. And now I start typing, and I say something like plot this, and now it will generate a it'll do all the right things to be able to make a plot of that function, and it'll show you the Wolfram language code here, and so on. Now, this is something we're doing. Not just, you can use this not just for math, but you can use it to do data science, you can use it to get demonstrations, you can use it for chemistry, and so on. And we see this as being a pretty interesting bridge between the world of Wolfram Alpha, which is zero documentation, drive by anybody can use it, and the world of Wolfram language, and will be increasingly leading people from Wolfram Alpha to Wolfram Alpha Notebook Edition, and and to let them build up notebooks that they can of computation. So this becomes a thing where, you know, you're doing your educational exercise, for example. It's not just a boom, you got the answer by using your phone or whatever, but you can actually build up the computation and understand what's going on. You can hand in this to a teacher. The teacher can send you a notebook that you can run. You can fill things in Wolfram Alpha Notebook Edition and so on. So we see it as a very important bridge from this zero documentation world, again, sort of achieving zero documentation and being able to get to something more like the Wolfram language experience. Okay, talking of education, big expansion in our Wolfram U domain, lots of new courses, lots of really, we kind of called it Wolfram U as sort of a kind of just a name, but it's actually turning into something much more like a university. You know, this year we issued so far 3,000 certificates to people who've taken Wolfram U courses, and we have an increasing number of courses that are really aimed at teaching domains of knowledge, making use of our computational capabilities. So we have a calculus course, we have an algebra course, we have, let's see, what else do we have here? Building and applying epidemiological models, geography, Wolfram language. We've got introduction to cryptography, introduction to differential equations, signals and systems, lots of things. We've got introduction to statistics, introduction to number theory. Pretty soon we're going to have, you know, a very nice collection of sort of university level and pre-university courses in Wolfram U, and we've been running this both as video courses, and we have study sessions and so on, daily study groups, etc. It's becoming a sort of serious educational resource, I would say. Talking of educational resources, we have continued to do our summer school. This is now the 20th year of our summer school, and you can see every time I think we're the only kind of summer school like thing that outright puts all the projects from the summer school up on the web sort of immediately, and they make kind of interesting reading, lots of different areas here, and we both have our summer school for grown-ups, so to speak. We also have a variety of other programs. This is our middle school summer camp. And then we have our high school summer camp, which we've been doing for a decade or so. And that has, again, it's really always quite impressive to see the kinds of projects that high school students manage to do in a couple of weeks with our technology stack. It's always pretty encouraging to see in terms of what what this idea of making a sort of computational generation, what this actually looks like on the ground, and what this sort of superpower delivered to at least these kids lets them do. It's always rather impressive to see that. I might mention that we also have our winter school. Part of the function of the summer school now is that we have tracks for the physics project and for mathematics. We have our winter school on fundamental science, which is really talking about multicomputation and things like that. That's coming up actually soon. Now, I mentioned in the summer camp, here's a little study we just did a couple of weeks ago, which I was just curious about. This is just random study of, it's kind of interesting demographic study. Those are the schools that the people who've come to our summer camp end up going to. And I don't know whether that's not our fault, so to speak, but it's I actually, one of the things I somewhat fear is that our summer camp has become sort of it is a very sort of successful summer camp, and I kind of fear that it becomes too elite, and we're trying to sort of work against that as well. But it's nice to see that we're giving people a good leg up to lots of interesting places. Let's see. So another thing that's happening there in the education area, we have this Wolfram Emerging Leaders program, WELP, which is has been extended to so it's now been made a more official program for high school students and also now for college students. It's doing group projects, supervised by our staff and working with our staff through the year, and that's sort of an extension of our summer programs and so on. I might mention just in the area of sort of learning Wolfram language and so on. One of the things we've also been experimenting with is kind of a mechanism. How do you learn a language? Well, you can use, I don't know, Duolingo, or you can use one of these online places where you're kind of presented with different fragments of language and you gradually learn the language. Can we do that for Wolfram language? We think yes. We think we can use natural language. We can use kind of what we humans are able to do in terms of natural language learning. We think we can leverage that as a way to teach Wolfram language. And so we're going to be building some capability to have kind of this kind of, I wouldn't call it drill learning, but I don't know what the right sort of polite term for it is, but this kind of way that one learns human languages. We think we can do that for Wolfram language, and that this will be a valuable thing that's sort of an adjunct to, for example, some of this project-based learning that we're doing in these areas. Okay, another domain, publishing. So our Wolfram Media publishing operation is apparently not found there. So let me just go. I think it's the dashes of killing these things. Let's see. Oh, come now. Maybe it doesn't have a dash at all. I'm sure there's a version of it without a dash. Okay, there we go. So we've had a variety of books. This is an introduction to machine learning, which you can also find on the web. Actually, we have another book that's coming, which this big, very heavy, boxed set of books of mine, together with this new one about 20 years of a new kind of science. And actually, these will be available at this conference. This is really heavy. I don't want to throw out my back holding this thing up, and it's anyway. So a variety of books. This is a book about mathematics that's based on a very interesting project that I'm not going to describe here, that is kind of merging the ideas of multicomputation and physics together with sort of the foundations of mathematics. I think it sort of a little bit redefines the last 100 years of what people have thought about as being the foundations of mathematics and metamathematics, but it is a different story. Let's see, in terms of books that we'll see coming, Wolfram community has been very active and energetic. Thank you to many people here who've been important contributors to the community. We hope to collect some topic-based books that are collections of edited versions of posts that have appeared on community, and hopefully some of you will have a chance to participate in that. I would just mention that in community, we've now got the really pretty good thing going of embedding Wolfram notebooks on the community. We have good SEO for those things now, so people can find them. That's all working well. Now, another area, another thing we've been doing, I've been doing a lot of live streams. I think in 2022 so far, I have apparently done 200, including perhaps an hour through here. And I've been doing actually it's a very interesting process. I mean, some of you may have seen our software design live streams. This is kind of like see how the sausage is made, but also thank you to people who've contributed on real time to suggestions on these live streams. And this is for us even, it's a great reference to go back to. Why did we design it that way? What was the thinking behind this thing? You can go and actually see the moment when that decision was made. I myself have been doing, well, a variety of other things I've been doing. This is a great way to learn how to explain things, I have to say. It's also a good demo of our technology of generating these word clouds of what I was talking about. But this is a weekly science and technology Q&A for kids and others. I guess I've done 105 episodes of this, where people ask all sorts of strange questions. And I get to be a progressively better explainer of lots of kinds of things, and I learn a lot from doing this. We've also been in our work in science, we've been very much trying to do this in the most open possible way, and I've been even recording video work logs where where I think they're I don't know, I haven't watched too many of them, but there we go. This is recording kind of when I'm working on things, I just record what I do. And so, you know, you want to know how that particular blog post was written and where that particular computation came from, you can go back and find it. And you can find where I actually created that thing. And within the post itself, everything is click to copy. So any picture that's within the post, you can just click it and get the code and find it. So we've also been doing from our R&D team has been doing live streams. We've so far only had 8 episodes, very small compared to the number of episodes I've done, but these are weekly R&D presentations and Q&A sessions with our lead developers and so on. That's another thing that's happening. It's kind of the beginning of sort of an office hours type mechanism for people to learn about and interact with developers in particular areas. Okay, another thing that is coming, and I'm almost at the end here. Another thing that is coming is, so we've been doing, okay, so in this whole thing about sort of artifacts from the future and what one can build with the technology and tools that we built, you know, I originally started building this stuff because I wanted to use it myself. And I've had the great pleasure of having a chance to do that over the course of many years, but in recent years, discovering that we can make immense progress in physics and in understanding the fundamental theory of physics, kind of the machine code of the universe, by using the ideas and the technology we've built. I mean, it's kind of shocking in the end. I didn't realize this till after the fact, but in the end, the model that we now have that seems to be kind of a representation of fundamental physics is actually a model that is very similar to transformation rules on symbolic expressions, although it's actually presented as transformation rules on hypergraphs. And actually, we've learned a bunch. We're starting to learn a bunch about how what you can get with hypergraphs that you can't get with tree-structured expressions and causal structure and all kinds of things like this. So the physics project is about to feed back through multicomputation and other things into the actual design of the language. But it's sort of ironic to me that these two things that have emerged for me personally, very different ways of language design and studying fundamental physics, have ended up converging on the same idea of sort of transformation rules for symbolic expressions, hypergraphs, that kind of thing. In any case, we've had this tremendous sort of flowering of opportunity to do basic research in the last few years, as a result of both the tools and the ideas that we built over the course of many years. And we've been doing a certain amount of that at Wolfram Research, at our company. But in the end, sort of the goals and motivation of basic research are a bit different from the goals of motivation of a technology company, which is you know, we're trying to deliver technology that's useful as tools to people, as opposed to do basic research that might have a payback only 100 years in the future. Or actually, and this is one of the weirdest things, the physics project, people ask me when we're doing this, when is this going to be applicable to anything? I said, expect 200 years. Turns out I was totally wrong, because we already have applications in these multi-computation areas and so on. We already have applications now of the ideas that came out of the physics project. So it's, but kind of the notion is to do things in the direction of basic science, even though we are well aware, like the things we'll be doing, some of the things we'll be doing will have quite near-term applications. But so in order to find a way to do that, we're trying to create a new structure And one of the things we've learned over the last 35 years or 36 years of this company is we learned a little bit about how to run an R&D organization. We've learned a bit about how to do managed R&D and deliver great results and find great groups of people to help deliver great results and so on. And so we want to take that methodology to basic research. In fact, I did that in building new kind of science. We did that in the physics project and so on, to take that methodology to be kind of a streamlined way to get basic research done. And so we're building a new structure for doing that, our Wolfram Institute, which will be actually launching next week as it happens. And thanks to our various financial supporters and so on, the Wolfram Institute, that allows us to basically do kind of sort of pure basic research for the sake of basic research. It's that we're going to be doing a variety of things there. First of all, in the physics project, we're really trying to get from our sort of machine code of the universe to things that the James Webb Telescope can actually go and look for, and that's a kind of a long, what in technology will be called a software stack, but in this case it's a physics stack basically to get from one place to the other. Also studying metamathematics, empirical metamathematics, trying to understand kind of the analog in metamathematics of questions that we can answer about physical space and so on. Also other projects that are, well, a bunch of upcoming projects in molecular computing, molecular biology, distributed computing, economics, etc. And we're looking forward to getting this going. As I say, it happens to be launching on Monday. And you can learn more about it actually from the live streams we'll be doing about it on Monday. Okay, so that's a new direction for us sort of in the basic research area. We fully expect that building on that basic research, as we've been able to do in the past, there'll be all kinds of interesting applications that become possible for us and for everybody else. Well, so this is a bit about what we're doing. I said at the beginning, one of the things that we really would like from you all is, we're doing these things, we're trying to sort of build the future. You all have given all kinds of input about that and all kinds of help, and you've contributed to this and so on. But part of what we really need to do is communicate that future to people today, so to speak. And sort of we really want to get help in doing that, because we can't successfully do that on our own. It's too much. The world's too big. We are too much concentrated on building the future, not enough concentrated on spreading what's there. And we're not, and in a sense, what the capability that you guys have is when you use these tools that we've built and spent the last 36 years building, you are kind of showing people you're being able to do great things with these tools yourselves, but you're also showing people what's possible with these tools. And many ways that we'd like to provide ways to engage with things. I mean, there's the live streams, watch them, comment on them, provide input, suggest things. That's one way to get involved. Be on social media, liking, sharing, submitting ideas and so on. Contribute to the community, contribute to the function repository, contribute to the Paclet repository, contribute to code source. Another thing is there are lots of public resources out in the world, whether it's collections of code or things about integer sequences and code for them, or pages on Wikipedia, or pages on other kinds of sort of information sources. Make sure that what we're doing gets connected to those things. Sometimes it's like there's a great picture that exists that is perfectly able to be put on one of those places, and nobody put it there. And it's like, don't assume, if it isn't there, don't assume that, oh, somebody else will put it there, because it turns out they don't. And if you can spend that 2 minutes and put it there, you're doing the world a service. And we appreciate seeing the things that we put so much effort into actually be out there and be helping people in the world. And we'd love to see that happen more. And that's something that we can't really do ourselves. And we'd love to see people help with that. Same thing is true with the stack exchanges of this world and so on. I also, for sort of the bigger things that people can do. We have a sort of a good pipeline for books, publishing companies. There are still publishing companies out there. They still do publish books. Books is still a good idea. And there's a lot of great books to be written that make use of our technology stack and that really make use of this computational essay type format. You know, I wrote this book, Elementary Introduction to Wolfram Language. There have not been as many books that use the template, which is available from that book, as I thought there would be. Very few, actually. It's a great template. I wrote that book very quickly. I think it came out pretty good. You know, other people can do this. When you write a computational essay, the good news is the computer helps you produce the material, so to speak. It's, you know, you're just providing the seed. You know, I myself am planning eventually, I've been saying this for a while, I'm planning to write some kind of introduction to the computational method kind of book, which is sort of an introduction, because one of the things that's an issue is how do people get to computational X? They just say, well, you know, I gotta sign up for a computer science course. Well, that doesn't even get you to computational X. You know, how do you get there? So we need to provide, and this is a great opportunity for people. I mean, the textbooks that get you to computational X, they will be used in every college. You know, this is something everybody needs. It's kind of the modern version of literacy, so to speak. And these things don't exist. We have the unique technology stack that really gets you to computational X without going through sort of low-level computer science. I mean, not that, I mean, computer science is a great field, and I love computer science and have tried to contribute a bunch to theoretical computer science and so on, and practical computer science. But it's not, you know, it's like many more people need to drive cars than need to know how to operate, you know, how to fix the engines of cars. And I think the, you know, there's a great opportunity to provide material that sort of gets people to computational X, maybe for all X, maybe for specific X, provides that material and provides that sort of educational path for people. It's important for the students who are, you know, signing up at universities where, you know, 80% of the people applying to some university want to study computer science, which is crazy. Nobody wants that. Not the universities, not, it doesn't make any sense. But what's needed is the material to get people to computational X without studying computer science as such. So that's an opportunity. I think just in terms of things people can do, hosting a local meetup, perhaps hosting a special interest meetup virtually. These are things people can do, and we have some mechanisms to help people make those happen. Another thing that we're trying to build the mechanism for this. We have a lot of students who want to, I mean, one of the great things about our technology, and maybe it's helped by the existence of Wolfram Alpha and things like that, we have a big flow of students who are very interested in working with our technology, our science, whatever else, but they understand, you know, this, you can get to computational X, they win the hackathons, they win the science fair prizes, all this kind of thing, by using sort of the magic of our technology, so to speak. And so there's lots of students who are interested in doing things, and there's a question of mentoring those students. And so one of the things that we'd like to see and we'd like to enable is a mechanism for people who maybe have been using our technology for a long time, maybe have even retired from their main occupation, to be able to connect with students who want to learn this stuff and you know, want mentoring, so to speak, to enable that to happen is something that we'd like to be able to see go on. And I would say that well, there's lots of other possible ways to engage. I think we're going to have some downstairs here. We have some sort of specific kinds of you know, of booths about different kinds of engagement, whether it's contributing to repositories, whether it's about some of these programs and directions that I've talked about. All right. Well, gosh, how long did I go on? This was sorry. We had so all right. So I've been telling you, you know, I'm excited about all the various things we're doing, and this is kind of a I've tried to give you a little bit of a taste of different things that are going on. As I say, the purpose of this conference is to give you a real version of this. I'm just giving you kind of the light dusting of things that are happening. But I would say that the big picture is, this whole idea of, 40 years ago or something of, let's make this full-scale computational language. Didn't frame it in that form. I've gradually understood sort of more and more clearly what it is that we're building. And I would say that, we're just in a great place right now in terms of having constructed this full-scale computational language across all these different areas, finding out the framework we've built, this old idea in a sense of transformation rules for symbolic expressions. That is just a tremendously powerful idea. The way I see it is, our goal, as I mentioned, is to sort of take what is computationally possible and make a bridge to what how we humans think about things. And it turns out this transformation rules on symbolic expressions is a pretty good way of modeling the kinds of ways we humans think about things. Maybe it has something to do with kind of the symbolic nature of language and things like this. But that's been a remarkably successful thing. We're now seeing kind of after 40 years or something, we're seeing with this kind of multi-computation direction, we're seeing a sort of a step up, which I hope will be accessible to us humans, of looking at that further. But in any case, I'm pretty excited about where we've got to. I would say the one thing that continues to be a challenge is we're building artifacts from the future, and we live in now. And can we do the service to the world of taking what comes from the future and delivering it now? And one thing that I've realized from the things I've done in both being around for a while and looking at history is these timescales are incredibly long. If there isn't real pushing, it's going to take 100 years. And that's a shame, because there's a lot of great things that will happen in the world. There's a lot of things that have happened in the world as a result of the technology and tools we've built. But there's a lot of things that won't happen for a really, really long time if people don't understand what's possible from the tools that we're building. And help us make that happen. We're trying to do what we can do in building the tools and in building communication channels, but we need help. Please help us. So, okay, thank you very much.